I'm going to talk about Glacier National Park uh, and the Rocky Mountains in which Glacier National Park resides. And some of in the background is a very typical photo of what you'd see in this long chain of the Rocky Mountains here displayed in Glacier National Park itself. You have these towering peaks with jagged uh, sides, uh, cliff faces, or scalloped edges, and, uh, and then you also see some layers here, which are actually sediments that were deposited in a marine environment, but now up here at elevations of say 10,000 feet above sea level. So the story I'm going to talk about is uh, from the beginning. How did you get these sediments in the marine realm? Then how did they come up to form to such high elevations to basically form the Rocky Mountains? And then finally ending with um, how you start to take these mountains down by the agents of erosion. In this particular case, where we are, because the elevation is so high, the glaciers have carved these mountains down, and all we see are the remnants of what has not been carved down by the glaciers. So, Glacier National Park is over here in northwest Montana. Um, and what I'm going to show you here is the left plot is color coded by elevation, and the right plot is sort of a shaded relief map. And what you can see is this is a common theme of a lot of the national parks out in the West, that it's situated in this really rough terrain here uh, that goes from Central America, Mexico, Western Mexico, up through the Western United States, all the way up into Western Canada and through um, Alaska. And this is really called we call it the Cordillera. The Rocky Mountains would be over here, but essentially the Rocky Mountains are just part of a long mountain chain that goes across the entire continental North America. And it actually goes all the way into Siberia and down into Eastern Asia. And here you can see the elevations get quite high, 3 kilometers high in some of these areas uh, in the North American Cordillera. And that really contrasts with the eastern half of the United States and North America, where it's relatively flat and gently at low elevations, gently sloping, for example, down here at the Great Plains, and then gently sloping down to the Gulf of Mexico uh, over here. So one of the themes of this talk will be about why do we have such a long chain of mountains here, youthful mountains. And Glacier National Park is just one nice place to see the history of North America in the mountain building process. So back to this slide. Um, what we're going to do is hopefully by the end of this talk, have a better understanding of why we have such high elevations and high relief in the Rocky Mountains, like here in Glacier National Park. Some more introductory slides to give you a teaser of what's coming. Um, this is up in the higher parts of Glacier National Park. Again, you got these high relief topography, but you'll see, of course, there's a lot of snow. And in the past, there had been much more snow that actually accumulated to the point that large glaciers formed that covered this entire valley, which does not currently have any glaciers, but it does have the remnants of a large glacial river flowing through, because you can see these lakes, which are sort of like scour marks, slowly built over geologic time as a big uh, glacier flowed downhill. And it also carved the sides of the mountain down, giving you these scalloped um, upper parts of the valley. Um, we'll also talk a little bit at the end about the flora and fauna of Glacier National Park. This is a mountain goat, one of the few places in the United States where you can see mountain goats. And they really like to be up there at the high elevations, the rocky terrains there above uh, tree line. This is another image we'll come back to. Glacier National Park, or the Rockies, uh, like I said, had um, massive amounts of ice in the region 18,000 years ago, what we call the last glacial maximum, or the ice age. Um, all that continental ice has retreated, and so all we have now is left of that is in Greenland, that ice cap on the subcontinent of Greenland. And so, but what we have now instead are more alpine glaciers. They're much more restricted in size. And so this is Grinnell Glacier. It's just a small guy here. And you can see the outflow part, uh, which is fairly restricted, forming a lake here. But this alpine glacier, over thousands and thousands of years, uh, gradually carves out this entire amphitheater that you see here, exposing these ancient rocks to the air so that you can hike on them and see them. This is another example of the agents of glaciation. Again, uh, the massive amounts of glaciation happened 18,000 years ago, so you're not going to see that. You just see the remnants, these alpine uh, glaciers up high. But this lake, and there's a number of them that are sort of elongated in shape. Uh, uh, those are the tracks, essentially, of where these rivers of ice have flowed down and scoured the basement, the foundation, and took those detritus downhill. And the end product is to generate these big U-shaped valleys. And you also see there are other U-shaped valleys that are entering this U-shaped valley, although entering it appears like as if they are floating or hanging. So there was a big ice sheet coming down, and then smaller order ice sheets that flow in from the sides, these tributaries of ice flowing in and reaching this big, thick ice sheet that made this this longitudinal valley. So Glacier National Park is in northwestern Montana, just at the border with Canada. On the Canada side, there's the conjugate parts of the national parks called Waterton Lakes National Park. I won't talk about that in such great detail because they're all related. But here's a map, and the closest town is Whitefish. You typically would fly in further south in, I think, Missoula, and then drive up. But you can stay in many places down in this tourist city. And you can see already within the national park. So this is a huge mountain range, and one part of the long chain of the Rocky Mountains. Here you can see here again with the high elevations in red. But you'll see these lakes, these long finger-like lakes. Those are glacial scours, and here you can see them as more evidently as long lozenge-shaped valleys. They connect upwards at the higher elevations. And all of these, essentially, you have to imagine 18,000 years ago, there was a big ice sheet covering this whole region, and it was flowing down by gravity, under its own weight, uh, down the sides of the mountains and carving uh, these U-shaped valleys. So we're going to talk about that. But first, we're going to talk about um, the substrate on which these glaciers are actually eroding or acting. So there'll be four parts to this presentation. As I said, we're going to talk about the beginning when this region um, of North America was actually below sea level, and it was in a uh, marine environment, a shallow marine environment, and you deposit a bunch of sediments. And then you fast forward in time, there was a time period about 100 million years ago that caused all of these sediments to be pushed upwards, thrusted upwards to form the Rocky Mountains and, and the mountains that we see in Glacier National Park. And then it'll end with, in more recent times, in the last couple million years, so which is actually very young in terms of the geologic time, we started to have the Earth moved into a realm of ice ages, and those ice ages began to take down the mountains that were built up to previously. And then I'll touch, of course, on the flora and fauna because that's something that is very near and dear to me. There's always a connection between life and Earth, or life and geology. So to I guess I'm going to show you here a map of geologic map of North America. Okay, and it's color coded according to the age of rocks that are exposed at the surface. And there's a bar chart right here, and the bottom corresponds to really old rocks, and the top corresponds to young rocks. So we usually think of the oldest being at the bottom, and things younger get deposited progressively, so you get younger as you shallow. And Earth's history is quite long. It's 4.5 billion years old, and so the reds or and the pinks, those are old stuff. They're older than 2.5 billion years in age, and you can see North America, its core, which is centered just beneath Hudson Bay, right here, is pretty red. And this is the ancient core of North America, 2.8 to 3 billion years old. And as you move outwards in all directions, you'll see it gets younger and younger and younger. It goes from reds to the purples and blues in this way. This green stuff kind of skips the purples over here, but really the purple sort of 300, 400 million year old stuff, that's actually underlying this green material, which are sediments, which we're going to come back to, that were deposited only about 100 million years ago on top of this blue. So ignore the blue, the green for a second now. What you have to envision, if I were to extrapolate these slivers of purple around, it would continue underneath all this green. So the continent is starts off long ago, 2.5, 2.8 billion years ago, and with time, it gets bigger laterally by new material being accreted on to the edges. So the red is the nucleus and just keeps on growing. And Glacier National Park is right about here, and it's in this place where all these purple rocks of 400, and actually in this case it actually does go to 600 million years, but 400, 600 million years ago were deposited. It was a marine environment, and then it was juxtaposed against younger rocks, this green material right here, which are also marine sediments, but formed at a very different time. And that juxtaposition, or the geologic processes or events that drove that, is what made the Rocky Mountains. So in almost all my lectures, I show the geologic time scale because time is so important when we're thinking about the time scales are so important when we're thinking about nature, natural processes. And for a lot of geologic processes, the time scales really are millions to billions of years. And this is just a cartoon version of a geologic time scale. And what it's showing you here, the oldest at the bottom, and these numbers are millions of years. You got 4.5 billion years or 4.6 billion years down here, and then 2.5 here. And then you start off here at 540 million years, which we call the Cambrian explosion. And every one of these different colors or names describes sort of a unit. The big ones, we call them eras, and the smaller ones, we call them periods. And each of them describe a window of time that has a characteristic faunal assemblage. And the boundaries between them correspond to a faunal turnover, typically a mass extinction. So for example, Permian to Triassic, a massive extinction happened in the marine realm. You don't see it as much in the terrestrial or above land, above sea level, realm, but the marine fauna just flipped over, went extinct, and then was flipped over to, as the niches open, new organisms kind of proliferated to fill those vacated niches. The same thing goes with the Cretaceous Tertiary boundary or the Cretaceous Paleocene boundary here. That was extinction of the dinosaurs. And when the dinosaurs went extinct, the niches opened, and the mammals and the birds could then proliferate. The mammals and birds actually existed with dinosaurs, co-evolved with them at the end of the dinosaur era, but they only exploded in terms of going all over the planet after the dinosaurs left our planet. And what causes these extinctions in every single one of these? Some of them we know, some of them we're not sure. But what is clear is there's always some sort of environmental change that causes a disruption to the Earth, global ecosystem at rates that are faster than global populations of animals in the ecosystem can adapt. That causes extinction, and then the Earth returns to a new type of state, a new environmental state, and new organisms take advantage of that. So our story, and the right-hand figure is just another way to depict the geologic time scale, just like in the form of like a clock. You go old 4.6 billion years ago, and you rotate around here until you get younger and younger and younger, and so forth. And this is just showing you key events in Earth's history of where there's faunal turnovers or changes in the environment and other events. And to put things in context, okay. And so this one's to scale. The one to the left is not to scale. Life as we know it, where there are macro scale organisms, multicellular life, large is really showing up here at the Cambrian explosion. Before 540 million years ago, you're talking about really microbial life. Bacteria are the dominant forms of life. You had some multicellular life in the 100 million years preceding the Cambrian explosion, but those are barely preserved because they don't form. So they were more like worms or things like worms. They're soft-bodied and they don't preserve too well. But they were there just before, waiting for the right moment, where environment changes, allowing them to kind of diversify into the life that we know it, all the life forms that we know today. And so it's kind of sobering that the life forms we know today really diversified only in the last 500 million years ago, so only a small fraction of Earth's history. And then humans, for context, you couldn't even see it on this scale. We're but a blip on the whole evolution of life and geology on our planet. So what we'll do, the story for the Rocky Mountains, and particularly in the region of Glacier National Park, starts in the pink, just before the Cambrian explosion, a few 100 million years before the Cambrian explosion. And at that point, we have this long period of time where we're in the marine environment and we're depositing sediments. And then we will fast forward to this period, the late Mesozoic, Cretaceous times, 100 million years ago. And that's when we have the building of the Rocky Mountains. Tectonic environments fundamentally change. And then we'll fast forward again, the Rocky Mountains persist actually through much of the Cenozoic. But in the last couple million years, we go into an ice age type of system for the Earth, and the ice sheets begin to grow and start carving down the mountains. And that would be in this time period up here. So let's go back in time and let's look at what Earth may have looked like 600, 700 million years ago, again, just before the Cambrian explosion. And so this is a artist's rendition of where the continents were at this time. And we have a general feel of where they are because we have ways of quantifying the ancient latitudes of these continents at a given time. We use the Earth's ancient magnetic field that locked in the rocks to get at it. And then we, like a jigsaw puzzle, each continent has different pieces that were formed when they were together, for example, and we try to reconstruct the continents by piecing those parts back together, just as if you do a real puzzle. And as you accumulate all that data, you can come up with some story along these lines. And so at that time, it was actually just after you had a big, what we call a supercontinent called Rodinia. Earth subdivided into a lot of tectonic plates on which the continents reside, and the plates are moving, right? They're spreading. Some places they're going downwards and subducting. So here's a spreading center, and here's a subduction where this ocean is going, sea floor is sinking beneath this amalgamation of continents. And because of that, these continents, as they move around on the plates, there are times when the continents are all aggregated together, and sometimes when they're all dispersed apart. When they're aggregated together, we call that a supercontinent. And this is a little bit after the supercontinent had formed and is beginning to disperse by the opening at that time of what we call the Panthalacene Ocean. And here's Laurentia, and that is North America. Okay, that's the old North America. And you can see a couple of things. As it was spreading, at that time, Laurentia was, before the spreading, was actually connected to Antarctica, so the west coast of North America. If you were sitting there at, just before this, you would have been able to walk over to Antarctica. But now we can't because it's split apart. And in that splitting apart, what it ended up doing is submerging much of North America, or Laurentia is what we called it at that time. And so this was a broad region where the entire, almost half of our continent was underwater. Not very deep. The oceans are about 4 kilometers deep, 4,000 meters deep. This may have been only 100 meters or so deep, 200 meters. But nonetheless, that's pretty deep when we think about lakes, for example. But this is what we call a shallow marine environment. And in the Cambrian, North America had then continued to split apart from the rest of the continents. It was sort of off on its own. And we may have had some interesting processes happen out on the western edge, subduction being out there. But again, much of North America was below sea level. It was we often think about continents as always being above sea level, but for lots of Earth's history, the continents, or a good fraction of them, were just below sea level. And we still don't call them continents, but you call them flooded continents. And during that time, when you had these shallow seas, the continents become repositories or depositories of sediments, of material from the uplands, because they're above sea level, and the rivers start to erode the parts above sea level, and they will transport that material to the low parts. And the low parts happen to be these inundated or flooded parts of the continents. And what you get is a lot of different types of sediments. What I'm going to show you are just a couple. These are the one on the left is a mudstone. It's a shale, and this would be shallow marine, fairly near shore type of environment, but further out than say like the delta. And here are you see these bumps here. These are actually ripples, and this is a 600 million year old snapshot of ripples at the bottom of the shallow sea. This would be formed by small scale wave action. We can also find in that area, if you go to slightly more shallow environments, you'll find these interesting formations. You see these layers, but they're arcuate in shape. Up is this way. You see another one here, sort of nucleating from here and growing outwards and so forth, like that. These are actually Proterozoic or 600, 700 million year, they call them stromatolites. And if you go to the Houston Natural Science Museum, they have a beautiful collection display of stromatolites. And stromatolites are microbial mats. They're made out of these microbes, algae, bacteria, and in a somewhat of a symbiotic relationship. They are typically very shallow because they need the sun's light to at least some of them need it for photosynthesis, and then some of the bacteria are there and take advantage of the food made by the organisms that are photosynthesizing. So there's a whole community, and each one of these layers, you have to imagine, was growing at the surface. I mean, between the water and at the base of the water. And as they grow, and then they die, a new layer forms, almost like tree rings. Some of this could be due to fluctuations in the water level as well, or nutrient levels. But over long periods of time, and we don't exactly know how long it takes to grow these, they grow very slowly, you generate these mounds, okay? And this is an example of the type of life that was there before the Cambrian explosion. Like I said, these are microbial mats. You don't really have a lot of multicellular organisms. Because actually, if you did, they may have had if there were animals, they would have grazed this material, and you probably wouldn't be able to grow such thick sections of these microbial mats. They would be eaten up or scavenged, grazed. Examples of modern day where you have these microbial mats are in Shark's Bay in Australia, Southwest Australia. And these are these algal bacterial ecosystems, micro ecosystems. They're growing. And you can see here's the top of the water. See the waves, and so they're just below. They can't be too deep. They're there so that they can see this. The sun's light can actually penetrate. And if it became too deep, they would die. If it became too shallow, they may also die, especially if they get above sea level. And so we think this is a modern day analog of these ancient forms of life that still, in fact, persist today. And here I'm showing you a picture of the Grand Canyon. I'm going to suddenly move out of the Rockies. And I'm doing this because the Grand Canyon is a place that is so familiar to most. And even if you don't know the geology, you know that the Grand Canyon is under what makes it so beautiful. Uh, in addition to this giant canyon, is all these layers of different sediments. And again, these sediments are also deposited in a marine environment, and they go all the way back. These are to the Cambrian right here, and down below actually to the Proterozoic in this region 600 million years ago. And even before that, you get to basement rocks of 1.7 to 1.4 billion years old. These are granitic rocks formed in a massive mountain building event. Then it went below sea level, and then the sediments got deposited. Okay, so in the Rockies, we have the same or analogous types of rocks. We don't see so much at Glacier National Park of this deep 1.7 billion year old basement, but it's there. You just have to go deeper. It's just not exposed. But we have all of this other ages, all these other sediments or history of the Earth. The only difference is in the Grand Canyon area, which is in Arizona on what we call the Colorado Plateau. That place somehow escaped this crazy mountain building, the deformation associated with the making of the Rocky Mountains. It still felt that influence, but it did not get all scrunched up. Somehow the Colorado Plateau is fairly stable, so all it did was go up and down, up and down. But in the area we're talking about, Glacier National Park, all of these guys were scrunched up together. And we'll talk about it later. And so they're all contorted. And you don't see, and so the history has been sliced and diced and flipped over to make telling the story much more difficult up in the Rocky Mountains and Glacier than in Grand Canyon. But they're actually analogous sediments. So there you go. You go from the Grand Canyon, you go up, same sorts of sediments, at least for the really early parts of the Grand Canyon, the deep parts. This is Glacier National Park. And now this particular section, at least they're still flat, but they're up at much higher elevations, and you have peaks, mountain peaks, whereas in the Grand Canyon, you don't have these sorts of peaks. Everything's flat. Okay, you're carving out something that's flat. So I'm going to fast forward in time because after the Cambrian explosion 500 million years ago, or a few hundred million years later, that region on the western part of North America was fairly quiescent. A lot of deposition of sediments. But in the Mesozoic, we developed a very strong, what we call a subduction zone, where the ocean basin here, the sea floor, is actually sinking beneath the continent. And that's denoted here by this orange line with triangles and or teeth, if you want to call it. And the teeth are sitting on the upper plate, and the other side is the oceanic plate and it's sinking. Okay, and that sinking here in the Mesozoic, and particularly in the late Mesozoic around the Cretaceous times, is manifested in massive mountain building in Western North America. And part of the reason for that is that we had just come out of this time period where we had another supercontinent, Pangaea. At that time, North America and Africa were connected together, and Antarctica was way out here. So these supercontinent cycles of opening, of continents coming together and continents splitting apart, they don't always go back to the same continent. They take turns and have fun with other continents. Well, Pangaea had all of these together. And about 200 million years ago, Pangaea started to break apart. And that was the beginning of the Atlantic Ocean. So here, 100 million years ago, the proto-Atlantic is growing. It's still narrow at this time, but it's growing. And as it grows, on the far side, we have subduction. It's pushing against that subduction zone here. and so you get a large mountain belt. Okay, and that mountain belt was associated with a lot of volcanism out west. Uh, what may be more familiar with you for that would be the Sierra Nevada in California, or Yosemite National Park, which is situated right in there. Those are the remnants of these 100 million-year-old volcanic arcs. And those continued north through Idaho and all the way up to Canada, into Alaska, eastern Siberia, and all the way actually down to Tibet in Asia, southern part of Eurasia at that time. Um, at the same time, what you have is on the backside of this mountain belt, you have the building of another shallow sea caused by deep mantle flow, dragging the upper plate down just a little. So if you go back to here, one thing to note is, interesting enough, all the continents are mostly above sea level, very different from back in the 600, 700 million year time period. The configuration I showed you, all the continents were blue. Now they're green, they're above sea level, except for a few places. And Western North America had this finger of flooding go up behind the Sierra Nevada through all of Texas and up into Alberta. Same thing with South America, although it may have been a little bit more restricted. So we call this an interior seaway. They called it the Western Interior Seaway. Okay, this is actually the place where everyone now is um, going after for fracking to get hydrocarbons out, or maybe not now because of the COVID and the oil and the energy collapse, but they were. This is where they were going. Okay, and so you were developing this basin in 100 million years, and all these sediments get deposited in there. And you have to realize that we also had 600 to 500 to 400 million years ago other sediments being deposited older. So those are still lying underneath here, and these sediments get deposited above them. Now, this is an interesting diagram from Snook and Chapman, a bit more accurate than my cartoon before, but I want to show you something very simple first. And here's where you have a subducting plate. Here's your Sierra Nevada type batholith and volcanism going on here. And then it is actually out here where you get these that subsidence that allows you to develop these shallow inland seas. But somewhere between that basin and this orogenic belt here, you have what they call a thrust belt, and they call it the Sevier thrust and fold belt. And what's going on here is, while this is going down and the Atlantic Ocean is opening, it's pushing the North American plate this way. So you're going to have compression in this upper plate. And this part, where all this magnetism is going to be happening, it doesn't want to go down because it's so buoyant, because it's relatively thick, a very thick crust. And the thicker you are, the more buoyant you are, and just won't go down. So what ends up happening is the North American plate is forced downward a little bit. And while it does go down, all the sediments that were built on it, these sediments, again, are those 600, 700 million year mudstones. They don't go down because they're not very dense. So they get stuck here. And so in this little regime here, and the consequence is as you try to push them, they're going to have to fail and deform. And so you get a bunch of these, what we call these thrust faults, okay? Forming a thrust fault is when you just, you're pushing and boom, you slide the crust upward. And you take old material or deeper material and thrust it above shallower material. And that's the key feature of a thrust fault. Okay. Um, Now, one of the interesting features of these thrust faults is that they can they can be very low angle, almost subhorizontal. Near the surface, they're steeper, but then they show as you get deeper, they sort of flatten out. And so these thrust faults are actually, you should think of them as uh, harboring the movement of a sheet that lies above it, and we call them thrust sheets. Very large, they can be on scales of hundreds of kilometers of, sheets of sediments that are just sliding up, on top of each other. And then there's a whole family of these nested thrust faults, and they're just moving uh, out like this. And you can envision that here you will get a lot of deformation, you'll get mountain building, and erosion will gradually take some of this down. So in Glacier National Park, it's actually subdivided into two mountain ranges. This is west and this is east. White Fish is here, and you would drive in to this region to the national park. This would be the cross section, and the western part is the Livingston Range. The right part is the Lewis Range, and most of what you're going to see, or all of what you're almost all of what you're going to see, are these Neoproterozoic or late Proterozoic and early Paleozoic sediments. All those layers deposited in this really ancient shallow sea. And further eastward at the time, you had these Cretaceous sedimentary formations forming by this younger tectonic activity. But this thrusting during this severe orogeny, that is the beginning of the building of the Rocky Mountains, by the way, what that does is it shoves these deeper, older rocks, in this case, these Paleozoic and Proterozoic sediments, upwards along a sheet, and boom, juxtaposes old rocks against young rocks. And so there's like 200 million years missing or so between these and here. So what you'll see is all these layers. They're not too deformed, but then out in the field, what you'll see is, if you look further down, um, the Cretaceous sediments. So suddenly you have old over young, which I told you when we do the geologic timescale, it's always the youngest ones that are more shallow, because that's where you deposit sediments. So the only way to disrupt that is through a massive fault. And so here is one of these big faults, and it's very low angle, almost horizontal, and it's um, elucidated over here. And erosion will eventually cut down here, and so you'll have windows into the lower parts of the plate, leaving behind these little islands of the thrust sheet that were that were continuous before. And we call these clipping, that are perched up there, still remaining. So here's an example of a clip. This is old Paleozoic and Proterozoic rocks, and down here are the Cretaceous rocks right here, and the Cretaceous rocks are a bunch of shales here. The old rocks include sandstones, limestones, which are a bit more resistant to weathering. And so you can see this significant break in slope. So the thrust sheet is right here. The thrust fault is at the base of the break of this slope. And here is another diagram from a friend of mine, Callan Bentley. He's drawn you the thrust fault, and all of this is this old rock, and all of this is the Cretaceous younger rock. So big thrust sheet push things over. And this is the primary geologic feature in, except for the glaciers, we'll talk about in a second, in Glacier National Park. And so it's that severe orogeny that builds up all this topography. And then after that, from 70 to 40 million years ago, there was the Laramide orogeny, which I won't talk about for the interest of time. But that continued to build up these mountains, taking them up to higher and higher elevations. Now, eventually, in on a planet with gravity, when you build something up high, it will come down, but it may take a long time to come down. So erosion, or the actions of rivers will erode and take down mountains through time. Um, in the Rockies and the Glacier National Park, um, they were at high enough latitudes and high enough elevations that glaciers uh, become one of the dominant ways of trying to take this mountain down. And glaciation, the Earth, for a large part of Earth's history, we didn't have that many permanent ice sheets at the poles. Earth was in a greenhouse state for much of its recent, history since 500 million years ago. This bipolar state where we have Antarctic ice sheet and the Northern Hemisphere ice sheet is really something that kicked in only about 3 to 5 million years ago. And I don't have time to get into exactly why that is the case. Um, I'm going to just fast forward and talk about the time that we became a bipolar world and we started to have these ice sheets. And these ice sheets become somewhat periodic. So the last time we had a large permanent northern hemisphere ice sheet was 18,000 years ago. Antarctic ice sheet remains. Um, and today, of course, we don't have that. All that remains of this last ice age, or big ice age, is the ice covering Greenland. Okay, so the ice has retreated all the way to Greenland. But during the last glacial maximum, or that last ice age, when the woolly mammoths lived, we had this big continental ice sheet over North America that extended southward to the Great Lakes and all the way into Montana. We didn't have so much in Eurasia, interesting enough, and that's actually related to the atmospheric circulation, which is which this circumnavigates up here, this polar vortex, but geology built a bunch of mountains in such a configuration that it causes that jet stream to not go around at the same latitude. It actually undulates, and it also causes the airflows to drop out the moisture in the form of ice or rain in different parts. And the way it happened was that in Eurasia and Siberia, it was too dry. The air masses already lost their water, so they really didn't develop big ice sheets there. It was only in North America and Fennoscandia, Finland, and Norway. And this is why you find in the tundra there permafrost so many woolly mammoths in Siberia. You don't get so much where we were because it was completely covered in ice. So just some background, why do we have these ice ages? First, I'm going to show you the record. This is some estimates of temperature through the last 400,000 years. And this is determined by drilling ice cores in Greenland or Antarctica. And these ice sheets go back actually a million years or so. And so they can drill downwards and capture these pieces of ice. In fact, we store some Greenland ice core here in the Department of Earth and Environmental and Planetary Sciences. We have a deep freeze freezer with Greenland ice. And you get the temperature from the chemistry of the ice or bubbles. They have air bubbles that are captured that will tell you, as I'll show you, how much CO2 and methane might have been in the atmosphere, and the composition, the isotopic composition of the ice, which I can't get into great detail for this, can be from that you can invert to get some estimate of temperature and maybe and also ice volume. And so what you see is here's today, and we are, in the grand scheme of things, geologic time, in a warmer period. The coldest time was 18,000 years ago, and then again 150,000, and then again 250,000, and then 350,000 years ago. So there's some cyclicity to this ice, these ice ages, and then slightly warm periods. And we think that to first order, that's controlled naturally by orbital dynamics. It's about how much energy from the sun makes it to the Earth and spread out to the Earth. So it's the solar flux. And that's related to the Earth's orbit because as it orbits the sun, the shape of that orbit, which we call the eccentricity, actually changes with time. On time scale is about 150 or 120,000 years, and that kind of coincides with this broad scale uh, periodicity. And the reason why it does that because there's as your eccentricity is changing, the average distance from the sun changes just imperceptibly amount, but just enough that the temperature can change just a little bit. And I'll explain to you a little more how that can trigger other effects that amplify that signal. Now we have other shorter term signals like the obliquity of the Earth, which is the tilt of the Earth. That matters because the tilt actually controls seasons, and because the Earth is asymmetric in terms of where the continents are, and the continents control where the life or the terrestrial life is, and how much ice you can form in reflecting energy back to the surface. There is an asymmetry to this to the effect of seasons and the sun's energy being truly absorbed by the Earth when the tilt changes. And the same thing with precession. That's the wobbling of the tilt axis. And those are operate at higher frequencies. And all of these operate within here, although it's really the eccentricity signal that is largely seen for the big ice age. Now you'll notice in the natural system here in the world that it takes a long time to get into an ice age, right? You go gradually cooling, cooling, cooling. And to get out of an ice age is very easy, very quick. Once whatever triggers getting out of the ice age, must be positive feedbacks that take you out of the ice age very quickly and melt all the ice. Now, what's not shown here is the very recent time, and I'll come back to that. You may ask, what does this have to do with the type of global warming that we're talking about today in the news from fossil fuels? And it's important, and I'll come back to it. But let me address a little bit about this asymmetry. And to do that, let me first talk about energy balance. And this is unfortunately somewhat technical, but all you need to know is this is the Earth down here, and this is the sun. The sun's energy, there's 300 watts per meter squared coming if you average over the whole Earth here. And what modulates this is the eccentricity. But once it comes into the Earth's atmosphere, some of it is reflected straight back out to space, and that the clouds reflect it, the ice sheets reflect it, the surface of the Earth reflect it, and we call that albedo, the reflectivity of the Earth. And all of those have something to do with, if you have more ice, the ice is very reflective. And so that actually ice is a positive feedback, reflects, and then you get more, and you get cooler. So less sun's energy is absorbed by the Earth, and you have more ice, cooler, more ice, and so forth, right? And so this is why the solar radiation matters. Now, once the sun's energy gets absorbed, it gets re-emitted as heat, infrared radiation. And the infrared radiation can then get absorbed by greenhouse gases, and we have CO2 in the atmosphere. and then that actually keeps the planet warm. Actually prevents it from freezing. Of course, too many greenhouse gases, it gets too hot. And so it becomes a balance between how much sun is coming, how much is being reflected, and then how much has been absorbed, and then how much of this infrared radiation is absorbed by the greenhouse gases and how much goes out. And the greenhouse gases themselves are controlled by the global carbon cycle of our planet, which is related to, well, today we have fossil fuel burning, but in the past it's related to life. Um, it's related to the circulation of the oceans that absorb CO2 and also exhale CO2. Uh, so, and all of those things come together in some interconnected system that makes it actually sometimes difficult to tease apart. So I'm going to come back to all of that, but suffice it to say is what happens is as you start to get to a point where the Earth starts to close solar radiation, insolation decreases, then you start to build these ice sheets, then the albedo increases, then the continental ice can grow a little more and kind of keeps on growing. And then finally, these ice sheets extend southwards into Glacier National Park. And then you start to build glaciers. The water that's evaporated from the oceans and gives you humid air, when you reach the mountains and that those rise adiabatically and cool, then the water pops out. And they're going to pop out as ice. So let's talk about glaciers. So up in the high elevations, is where you get the precipitation. And, this is, we call this the zone of accumulation. And as the ice builds up, because it's essentially heavy, it will start to collapse under its own weight. And that's when what we call the beginning of the glacier forming. So a glacier is ice. It's actually a rock. It's a rock flow, but the rock we call ice. And although you think of ice as being brittle, over long time scales, over years, the ice actually flows like taffy, and it will flow, of course, downhill. And you can envision that as it gets, that piece of ice gets to too low of elevation, where it's a little bit warmer, and ice is not stable, then it's going to start to melt or it's going to sublimate, and that would be over here at the toe or the foot of the ice. So this is where you build it. This is where you evaporate or melt it. And when things are at steady state, so the equilibrium line kind of defines the point where accumulation and loss are equal. But at steady state, there's no advance or retreat of the ice sheets. And you can envision that the ice sheet can advance if there's much more precipitation. So it's colder or more humid, it advances. If temperatures rise, then it'll retreat as the zone of accumulation retreats uphill. Okay, so this flow of the ice sheet does a lot of interesting things. Ice is a rock, and although you can crush it in your mouth, it actually is strong enough. Again, over tens of years, thousands of years, it scrapes against the rock. It wedges itself, the ice, into cracks, and as it expands, and the water in there, it breaks the rocks. So what typically happens is the ice is a very effective erosional agent. It carves out the mountain, and so it'll generate up in the head ice or headwaters. It generates a cirque, an amphitheater-shaped valley, because it's basically scalloping, spooning, or carving out the mountain. And then it goes down, and as it goes down, it's plucking rocks off from the bottom and transporting them within the ice. And so it carves a valley, and it keeps carving that valley deeper and deeper and deeper. And that valley is going to be in the shape of a U, quite different than a river carving out the valley, which will be more like a V. Okay. As you get down into this region, in the toe where you're ablating, right, you're evaporating or melting, all that detritus that's carried in here, that it plucked, now falls out of the system. you form a lake, but you form all that detritus gets dumped out here, and it forms like a dam. This thing is called a moraine, a terminal moraine. When two glaciers come together or on the edge of the glaciers, you also get dumping out, and these are called lateral moraines. Okay, um, and then eventually some of this water that builds up here will breach these moraines, and you'll have some braided river channel come out here. So some of the key vocabulary: you have a cirque, you have the moraines, um, you'll have these jagged peaks, and that often happens because on the other side of the mountain there's another glacier, and they're both scalloping, carving, and so eventually you have this very narrow ridge at the top, and a lot of series of narrow ridge at different scales, and these little horns are what we call arêtes. And it's French is because a lot of this cirque comes from this terminology came from the Swiss the studies in the Swiss Alps long ago. So here's a cartoon of what we could envision of a glaciated topography during the last glacial maximum. This is the pre-glacial topography, which is carved up in this sense by rivers. So you have more V-shaped valleys. But with time, ice sheets grow, and you get a very big glacier in the big valley, and carving out a U-shaped valley. And then these rivers now become tributaries for other ice flows to grow, but they're smaller and they flow into the bigger ice flow. And this one is really carving deep down into the bedrock a deep valley. And these guys converge at the surface of this glacier. Now, when it melts, the melting, as I showed you before, when you get out of a glaciation, it happens very quickly. This getting into here takes time. Getting out is fast. So the ice sheets retreat, melt, and so you suddenly leave you take off the veil, and you have this subterranean, this glacial topography exposed now to the surface, which is what you see in Glacier National Park, U-shaped valleys and these hanging valleys of glaciated valleys that come out. And you'll have these beautiful waterfalls now because it's a fluvial environment, but they take advantage of the glacial valley and then they cascade down into this deep basin, a deep channel, glacial channel. And here is I took this from a talk I gave for Yosemite National Park. We're not talking about Yosemite, but the same concept. I just do that for familiarity. Yosemite Valley, a big ice sheet, ice flow, and then you have these hanging valleys coming in. Today, we don't have any of those big ice flows in Glacier National Park. They already disappeared 15,000 years ago, and what we're only left with are these alpine glaciers. They're just the remnants of it, and we'll come back to these alpine glaciers because they are now shrinking on our human timescales. So when you go to Glacier National Park, you're not expecting to see something like this because those really were already gone from about 15,000 years ago. The really long ice sheets there. But I'm going to show you some modern ones from the Swiss Alps, and this is a perfect example of one long flow that's carving this U-shaped valley underneath. And then you have other flows coming in from the sides here. There. Okay, so we still see these in the Swiss Alps because there's a lot more moisture there, and so there's still much more building of these glaciers. But even those right now are shrinking. This is a picture of one of these glacial valleys with a bunch of little lakes here. And it's just, this is just the effect of glaciers scouring inhomogeneously along the way. And when they retreat, you'll have little dimples This is an old picture from the early 1900s, where uh, from Grinnell Glacier, actually in the national park. And this is showing you a small moraine. So this is an alpine glacier, though. And you can see the ice sheet, the glacier was here, but it retreated a little bit, and then dropping its load of detritus that it picked up along the way. Um, Here's another, this is down the valley. You can hike up here. This is a glacial valley formed 18,000 years ago. And then what you have now, or in modern times, alpine glaciers up here forming cirques. And they sort of hanging, they form hanging valleys up here, and then now they're in the form of waterfalls. Here's another one. This over here is a from the last glacial maximum valley, U-shaped valley, and then over here were some tributaries of ice flows that went into this bigger channel. And then after the ice sheets retreated, you left this area stranded, and all you have now are some remnant glaciers up in the highest reaches of these channels. These are arêtes here. You can think of this as an arête. There's glaciation on the other side. Here's some more arêtes. Each one of these little scallop valleys, there was a small alpine glacier. And they just carve their way, and they just leave some almost like spines of uneroded or unglaciated terrain there. So coming back to the orbital dynamics and this asymmetry, let me talk about that. I'll show you, I should have shown you this earlier, but these are the ways you actually drill down to get this ancient or this paleo record of climate. You go to the ice sheets. This is the Vostok one in Antarctica, and in Greenland they have a few places you can get ice cores, and they actually use hot water to help drill down, and then they come out with these beautiful cores. And from these, like I said, the chemical compositions of the ice tells you something about temperature. It's the oxygen isotopes, and then gas bubbles or air bubbles trapped in here give you a piece of ancient atmosphere entombed, encapsulated within this ice. Okay, and this is what you get when they have the temperature. Okay, present day is here, so 18,000 years ago is when we were really cold, the ice age, and we are now in a warm period. Yeah, but what's also plotted here are the methane concentration in the atmosphere back in time, and the carbon dioxide concentration. So our pre-industrial values of CO2 are about 300 ppm, although now we're quite a bit higher, and I'll come back to that. But you can see that in the glacial periods, ice ages, the CO2 values were only about 180 parts per million. And methane levels were lower too. So they kind of go together. It's pretty remarkable here. And what's going on is that when the temperature changes, so say you warm, there are feedbacks that then go into the carbon cycle. And so, for example, when you warm up a system and get out of it, what happens is more CO2 is released, and that CO2 becomes a greenhouse gas, and then that accelerates the warming or amplifies the warming. And the same thing when you cool, um, the CO2 levels go down, and that amplifies the cooling. Now, what appears to happen is that the amplification of CO2 being released back into the atmosphere is much stronger when you um, uh, deglaciate, when you start to warm. And these right here, I'm only talking about natural processes. And so why do you have these feedbacks? Well, it has a lot to do with a couple of things. One is the terrestrial system, and the other one is the marine system. The ocean circulates on time scales of about 1,000 or 2,000 years, and it's flowing. And these curves here kind of tell you how the ocean masses and water masses are moving um, around. And the reason why they circulate well is because of density differences within the water. And one of the two things that control density is temperature and salinity, how much salt, how salty it is. And one of the biggest controls really is the saltiness. And the saltiness is controlled in these open oceans by whether you have ice, particularly sea ice. So in the North Atlantic or around Antarctica, when you build a lot of sea ice there, uh, which in many cases today is now just seasonal, but in ice ages it's more permanent. Uh, when water freezes, it expels all the impurities like salts, and the ice is pretty pure, pure water. And so the water just beneath the sea ice becomes saltier, and then it becomes quite dense, and then it's cold because the sea ice forms at the polar regions, and then it sinks, and that starts this ocean conveyor belt moving there. And when it sinks, it goes down, and it eventually comes back in certain areas. And for example, in the southern hemisphere around Antarctica, this is where you build the Antarctic bottom waters from the salty waters going down from the sea ice. But the sea ice from the North Atlantic is rushing down this way. Okay, it's not as dense as the Antarctic waters because those are saltier, and and then it comes up here. Here are the surface waters from the circumpolar current, and it can leak out here around the Antarctic region. Now, why that's important is these waters, okay, as they are sinking from the North Atlantic and they circumnavigate the Earth and then eventually come out here, they're old. By the time they come out, they've been deep down in the water for a long time. And one of the things that happens is they build up dissolved carbon dioxide in here. And that's because there's all this organic matter, living organisms up here in the shallow waters. And when they die, when they're alive, they're doing photosynthesis, and they take CO2 from the atmosphere and incorporate it into their bodies. And then when they die, they sink. And when they sink, they come back down here, and then they decay, become consumed, and they redissolve back into the water. And so these deep waters, the old waters, are enriched in CO2. And then when they come out to the surface, they exhale that CO2 to the atmosphere. And so the ocean can be a sink for CO2, and it can be a source for CO2, depending on what time scales you're looking at, and depending on whether you've perturbed it out of its system, of the steady state system. So what happens is when you suddenly change the temperature a little bit, it changes the way the ocean may circulate a little bit and how efficient this degassing of CO2 is. And that causes a cascades of effects that can amplify, say, the warming. And when the CO2 comes out, you warm much faster, and you have a runaway, almost a runaway. This initial warming can also cause permafrost to melt, and the permafrost is storing carbon in it. And when the permafrost melts, that carbon now is allowed to degrade and then go back into the atmosphere. So there's also a terrestrial feedback there that amplifies. And these are all natural processes, responses, I want to say. Okay. Um, so just remind you that this is what the ice cover looked like in North America during the last ice age. And, uh, and I'll come back to uh, why I want to talk about those feedbacks, why these natural processes that get you out of the ice age accelerates the process. Um, so I'll get to that again, but I just want to show you as an aside, when we had those big ice sheets, not only did the ice extend further south, right, but um, sea level was lower because you stored so much of the water in the polar ice sheets. So if you live in Texas, like in Houston, you're very familiar with Galveston Bay, right? Well, Galveston Bay actually is a remnant of the last ice age. And the reason is when sea level was lower, um, the coastline was way out here at this, what we now call our continental shelf, out almost 100 miles out, I think, here from Houston. Imagine that. If you were here, you would not have coastline real estate. But as the ice melted, or before the ice melted, when you have the coastline out here, the Trinity River and all these other rivers here were incising out to get to the ocean. So there was a canyon or a valley, not very deep, but there was a valley that went all the way out. And you can even see the remnants out here at the shelf uh, uh, to the continental shelf, to the margin. But when sea level rises, that water then uh, migrates this way and fills those valleys, giving us these bays. Okay, that's exactly why we have bays in Texas. San Francisco Bay is another example in California of a valley that was developed during the last glacial maximum and then filled. The valleys filled uh, after they melted, and so you have the San Francisco Bay. Other effects of the lower sea level was that the Bering Sea area was exposed, and you could have migration of people and animals across Eurasia and North America. So a lot of interesting effects. Now I'm going to come back to the glaciers in Glacier National Park. Like I said, um, don't think when you go to Glacier National Park that you're going to see these big ice flows. Those were around 18,000 years ago. They're long gone, and they have nothing to do. The fact that they're gone has nothing to do with anthropogenic effects. What uh, what may have something to do with anthropogenics are the effects of climate change on these remnant glaciers. So you go there, you'll have all these alpine glaciers that are still left over from the ice age, like Grinnell Glacier. So you know, 30 years ago, you can go and see them. And now this is a time lapse of Grinnell Glacier, and you can see here in 1938, you had that, and you had this was all ice too. 1981, the ice, this glacier has retreated, and now you have a glacial lake. 1998, here you are again, the glacier lake is getting bigger. 2009, the Grinnell Glacier is really shrunk, and all you got is this part here. 2015, it's just about gone, okay? And so it's these alpine glaciers in the national park that are that we're really concerned about, or evidence of something is going on. Probably within when my child grows up, he's 5 now, there will literally be no glaciers left in Glacier National Park, not even these alpine glaciers. What's causing that? Is it global warming? I don't know, but I will show you some. Oh, here's Grinnell Glacier again. This is from 1910. This is pretty much today. Look at this. That's all you have left of it today. Back then, it covered all of this. And you can see the evidence of it was actually flowing down the slope because you see these crevasses, extensional tensional cracks as as the ice body is sloping downwards, or sliding downwards, is cracking at the surface. Now you got this. That's it. You got a nice little lake to go to. Of course, if you're a geologist and you want to see the stratigraphy here, it's good for you. But if you want to see glaciers, not so good. Here's the Jackson Glacier in 1911. That one actually was pretty nice with a fairly good size ice flow, a glacier. Now, nothing. You've exposed the bedrock, 2009. So there's not much left. And if things keep going the way they're going, there will not be any glaciers for our kids to actually see. So I'm going to take you now to Hawaii just briefly. You're going to say, well, why am I going to go to Hawaii? Well, Hawaii is a volcanic island in the middle of nowhere, in the middle of the Pacific Ocean. And you may not realize that although it's in the middle of the Pacific Ocean, fairly low latitude, tropical environment, right? The main island here goes up to very high elevations, 10,000 feet or so. That's about as high as some of the mountains in the Rockies. And so you can have snow up there. And in fact, during the last glacial maximum, there were also small glaciers in Hawaii, way up at high elevation. Well, one of the nice things about being out there isolated is you don't have light pollution. You don't have a lot of pollution from humans. So people like to put observatories there. So there's a big astronomical observatory. But there's also atmospheric observatory, which is to monitor the composition of the atmosphere. And this scientist named Ralph Keeling, back in the 1960s, had developed a method for precisely measuring the CO2 concentration in the atmosphere. It was a very difficult thing to do at the time, to get it precise. And he decided he would do this in Mauna Loa in Hawaii because if you try to do that in Houston, you're going to have perturbations from car exhausts and all of that. It'll vary by day. But if you go far away from humans, you get a measure of the atmosphere. And the atmosphere is fairly well mixed as long as you're not down in downtown Los Angeles or Houston, but it's mixed. And so you can get a representative view of how much CO2 is in the atmosphere. So when he started this, this is what he got in 1960. Okay, there was increasing, but during that time you couldn't really say so much because it only had a short record. And but eventually he retired, and the record was continued by his son, and then continued by others. And so now we've got this record from 1960 to 2020, which I don't show here. And here there's clearly it's been increasing with time. Now these jagged aspects are related to the seasons, and related to the terrestrial biosphere that is, and because there's more land in the northern hemisphere, in the winter you release CO2, in the summer you consume CO2 because of photosynthesis. If the Earth was completely symmetric, you wouldn't see these ups and downs, because all the land, almost all of it, is in the northern hemisphere. It has a very strong northern hemisphere bias for seasons, and that's why you see that bumping up and down. Okay, but ignore that. What you want is this long-term trend of rising CO2 from 320 to now 390 parts per million. Now, 300 parts per million, 390, is, if you go back to the time of the dinosaurs in the Cretaceous, the time of the Cambrian explosion, that's nothing. The CO2 levels were much higher. And so Earth indeed had higher CO2 levels and was warmer, and the life was fine. Okay, but it's not so much the absolute that is the issue for us. It's the rate of change. So this is the reason why I showed you that ice record before, through the last 400,000 years, and this is all natural. Okay, but now you superimpose this current rise in CO2 of what we're seeing now over the last 60 years or so. It is shooting up, right? And it's actually higher than we've ever had, in fact, over the last million years. And human evolution only happened within this time period, or humanoid evolution. And so we are seeing the highest in the time periods where we have been comfortable in And more importantly, we're seeing it happen at a rate that is unprecedented, never happened at this rate before. What's causing this? When there, people debate it, um, but it's pretty clear. I don't think anyone would disagree that what's causing this rise in CO2 is related to fossil fuel combustion. It's simple math and simple physics that when you have fossil fuels here, you burn it by adding oxygen to it in your engines, you generate CO2 and you go up. And you can actually uh, compare the total flux of CO2 uh, in the natural environment to our fossil fuel burning right here. And you can see it is pretty large there. So I don't think there's any doubt that the CO2 is recent rise is caused by fossil fuel burning. Even the climate skeptics, I don't think, disagree with that. The only disagreement is what is the impact of this higher CO2 on temperature, precipitation, and all sorts of things. And there indeed is a lot of debate on that. Now we will see, of course, that temperature has also been rising with time. There are some bumps and here, but overall it seems to track the CO2. Now, as a scientist, I'm always wary of, of the difference between correlation and causation. So I'm not going to tell you that necessarily that this rise in temperature must be controlled by CO2, which is controlled by fossil fuel burning. I leave that for you to think about. But what you want to go back and look at is that the rate of rise is unprecedented, and it's the rate that we have to worry. And even if one doesn't think that this has anything to do with fossil fuel burning or due to humans, and it's a completely natural thing, which I don't think so. But even if it is, the rate at which it changes is something we've got to deal with. If it's fossil fuel burning, then we need to think about how to reduce emissions. If it's a natural thing and if it's a fossil thing, either way, we have to deal with the consequences. And so it pays to do research on this to figure out what's going to happen with this and how do we need to respond to mitigate or to adapt to these changes that are inevitably going to happen within our lifetime, within our children's lifetime. So I will end now with fauna and flora, and I'll come back to this nice image of elevation. Western North America has high elevation, the mountainous part of the country. And superimposed on all this on the right is a rough breakdown of the different biomes of our continent. And the biomes are controlled largely by a combination of temperature and precipitation, rain. And so there are zones that are really related to geographically where you are in terms of precipitation and temperature. And then there are zones that's where precipitation, rain, and temperature are controlled by elevation. So you can see that this green thing right here, this dark green, which they call the Northwest Forested Mountains, right? They kind of follow the Rocky Mountains, the high elevations. The highest elevations are here. And so it's mostly in the Canadian Rockies, but extends down to Montana and into the Colorado, Central Colorado, and actually even down into Mexico, okay? Because the elevations are high enough. So the Rocky Mountains, if you want to think about it, really go from Mexico all the way to there in terms of sort of the ecology to some extent. And so what you'll see is some of the types of environments, if you're down in the valleys, you'll have a lot of aspens, deciduous trees, beautiful trees. If you go to slightly higher elevation in the coniferous forest, you'll get a lot of lodgepole pines, which are often the first ones to colonize after a fire. But then you can have hemlocks, and these tend to form very dense, thick stands of forests. where light doesn't really get in, and this would be considered a fairly mature forest, but ready to burn as well to start the cycle over. You get to higher elevation, you have the fir, subalpine fir forest, type of pine tree, and even higher you have the white bark pine in the region. So Glacier National Park is really covered by pine trees, and interest in the mountains, and then above that you have above tree line you have just rocky, almost like tundra type environment, and then below in the valleys you'll have open grassland and willow lined rivers and riparian areas. So I'm just going to give you a quick tour of some of the animals there. The Yellowstone National Park is probably the best to see mammals. And then after Yellowstone National Park, I'd say Glacier National Park, maybe the Rocky Mountains would be the next really exciting places to go if you want to really see mammals. At Glacier, it's one of the few places where you can see grizzly bears. You, of course, have to be very careful. You don't want to get caught between a grizzly bear and their cubs because you will probably die. Um, you have a decent chance of seeing them. You have a chance of seeing coyotes, and if you're lucky, maybe even the gray wolves, which were really almost driven out to extinction within the lower 48 states, but have come back in Montana and Wyoming. The mountain lions are a fixture of the region, but highly unlikely you'll ever see one because they're very secretive, nocturnal sort of animals, and live more in the remote parts of the park. What you're more likely to see are the ungulates, the hooved animals. There are bighorn sheep and Dall sheep. Dall sheep much higher elevation. The bighorn sheep, a family often sits at the Continental Divide area, which is a great tourist spot, and you can usually see them there. They're a sheep that likes to live on the rocky mount cliffs. At the higher elevations, less vegetated, you'll get the mountain goats, and they are even more agile on the cliffs. You probably will only see these off at the distance, the little white blebs on the cliff faces. In the valleys, you'll get the elk, and of course, there are moose in the region, in the valleys, especially around water, as they feed a lot on the aquatic vegetation. While you're there, always pay attention to some of the rodents. The common ones are the beaver. You'll certainly see the evidence of the beavers in the rivers, the dams that they make. Golden mantle ground squirrels will be running around in the campgrounds. Hoary marmots will also be around. In the high elevations, one of the things to look out for, and this is one of the more peculiar guys, is a rodent called a pika. It's a small rodent, almost tailless, and it lives really in the most rocky parts of the areas and above tree line. They make some very loud, squeaky noises, so you use that to alert your attention to their presence. A cute little animal to look for. I like birds, so I'm going to show you a little bit of the birds you might see there. In the lowlands, trumpeter swans. Not too many places where trumpeter swans breed in the United States, but here they are, and also in Yellowstone National Park. This is also a good place to see the common loons, yodeling in the summer. One of my favorites is the harlequin duck, which is really a sea duck in the winter. It winters off the rocky coasts of Washington or Northern California and off of New England. But in the summer, they actually go up and inland into the mountains, the Rocky Mountains, and they breed on the rocky rivers, the rocky streams, these cascades. So they switch from a marine environment to this freshwater alpine sort of riverine environment. I've always found that myself quite peculiar. Other birds that are around, it's a great place for owls. There you have the saw-whet owl, which is a small guy. And then you have the biggest owl that we have in North America, which is the great gray owl. They'll be found in mountain meadows, and that's a diurnal owl. So you can see them during the day. You have to be patient, quiet, and just really pay attention to your surroundings to notice these. But they're there. Um, Other curious creatures that are there are these chicken-like birds in the forest, the spruce fir forest. You'll have the spruce grouse down below, which is related to a quail or chicken. And they blend in with the surroundings very well. But in the spring, you might hear them making their very loud mating calls. If you go up above tree line, um, you will find you have the potential of finding ptarmigan. Uh, this is a bird that's often hunted for its meat. It's a beautiful bird. In the winter, it becomes all white. In the summer, it changes its plumage and blends in with the rocks and the small shrubbery. And these ptarmigan, they're there, but they're very camouflaged. And so you have to look very carefully if you want to see these. And other birds there in the forest themselves, the beautiful western tanager, which I never get bored of, the white-winged crossbill that feeds on the cones of the firs and the spruce, and the Canada jay, which is very common, and that will come down and probably follow you around if you're eating lunch, hoping to get a snack from you. They're very tame birds. Used to be called the gray jay, but now more aptly called the Canada jay because their range is mostly in Canada. So I'm almost done, but I'm going to show you this figure here about the biomes again and the elevations. It's an example of where really geology and geography control the distribution of life. So biogeography is what, if you want to call it that. And I'll give you examples here that there are interesting warblers of the Dendroica or Setophaga subspecies. They used to be called Dendroica. And there's one here, the hermit warbler, is following the Rocky Mountains here and down into Montana. But then you have these other guys that are very closely related, and we think that they recently split because of all this glaciation from the last glacial maximum, causing them at the time of the last glacial maximum to be more contiguous in their distribution and one species. But as the glaciers retreat, you generate all these different islands, the Rocky Mountain chain, and then this inhospitable area here for these particular birds. And then these guys are in these pine forests, so that would be the black-throated green. And then the guys that get stranded down here, that didn't go with the retreat of the glaciers, they're the black-throated gray warblers. They've adapted to being in more pinyon juniper. And then the Townsend's warblers moving off over to the Pacific coast. We also have, if you look at this black-backed woodpecker, look at the range here. It likes a particular type of tree, these spruce trees, and you'll find them in the North American taiga. So they occur all across the taiga here, but they finger down all the way into the south where the Rocky Mountains, these high elevations, still retain remnants of the taiga forest, okay? So the Sierras here and Northern Sierras and the Glacier National Park area. The same thing goes with the gray-crowned rosy finch, where the blue is just a winter range, but the purple is where they breed, and or permanent residence, and then the orange is where they move out towards in the summer or spring. And you can see the stronghold is here in Glacier National Park area. And again, probably during the glacial maximum, they were much more widespread, but they retreated to these islands of coniferous forests in the high elevations. So with that, I end my talk with this nice image of Glacier National Park. And now you can see this glacially carved landscape. The rocks themselves were these sediments deposited 600 to 400 million years ago in a shallow marine sea. And then they were uplifted around 100 million years ago and thrust over younger rocks. And so what you're seeing is this mountain is this big thrust sheet, built up this mountain. And then uh, over time, it's been coming down through the agents of erosion, rivers. But then now, in the last several million years, it's been taken over by um, ice sheets that start to carve the mountain down. And so there were big ice flows here, and that was the last glacial maximum 18,000 years ago. They've all since retreated except for remnants of them that are perched up high as alpine glaciers. And with recent changes of global warming, whether you think it's a anthropogenically induced or not, doesn't really matter. Global warming has happened. That has been causing the retreat of all that remains of these alpine glaciers, and most today are gone. So the average tourist going there with the accessible roads will never see the glacier anymore. You'll have to hike far deep in to see any remnants of the glaciers. And they may not be there for our children. So I hope I've given you a story of the Earth through looking at all these rocks, and I hope I've given you some insights on how life and Earth interact through these lectures, and finally giving you some ideas, some thoughts for hope, as well as some things to think about that we must be concerned about. And so hopefully you can now see the Earth as a much more interconnected system that we want to be part of and take care of so that we can experience it better and have it take care of us better. Okay.